Mrs. Rickles.
Well, good morning. I've got your email this morning, and I have just the experiment for you. I have it all written down here. Here you go.
Thanks, Mrs. Rickles, for helping us.
You're welcome.
It looks like we need to go outside and create echoes and measure how long it takes us to hear those echoes. Let's get started.
Okay.
Okay, everybody line up in threes. One person will do the clapping, the other person will time the number of claps, and the other will take the data. We need a set of pipes, a meter stick, a stopwatch, a pencil and a paper, and goggles. We will use the side of the building to bounce sound off to create an echo. Measure 57 meters from that wall. I can do that, but I need help. Okay, you need to stand right here. This is where we'll start the experiment. You need to start clapping these two items together like this, and listen for the echo.
You really need to get a rhythm going so that you can hear the echo in between claps like this.
Let's try it.
That's good.
Okay, I'm hearing the echo. Let's time the number of claps in 20 seconds and record our data so we can analyze it when we get back inside.
I have 30 claps.
That's great. Let's do the experiment again so we can take an average of the number of claps. Remember, when you are experimenting, you must have repeated trials. In the sting problem, we learned that we need to perform the experiment at least 3 times. Okay, we need another group to line up. Let's count down. 3, 2, 1, go!
Do you know why it's important to take an average?
Taking an average helps us to eliminate the possibility that someone counted wrong, read the stopwatch wrong, or didn't understand the instructions. Do you know how to calculate an average? It's easy. For example, you can take the numbers 20, 22, and 19. You add them up and divide them by 3, and that's your average.
Now, to calculate the speed of sound, we need to take the number of seconds and we need to divide it by the number of claps. This is going to tell us the amount of time between claps. What do we get?
That's 0.66. Let's see, I calculate that to be 2/3 of a second between claps.
Okay, we have 2/3 of a second between claps, and the echo comes halfway between claps. Then it only takes 1/3 of a second for the sound to travel to the wall and back to us.
I guess that sounds correct. And to figure out how far it travels from us to the wall and back, wouldn't we just take 57 meters and double it? What? 114 meters?
Correct. Now to figure out the speed, divide distance traveled by the time. Okay, that would be 114 meters divided by 1/3 of a second. That comes to 342 meters per second.
That's beyond fast.
A meter is just a little longer than a yard. This means that sound travels more than 3 football fields in a second.
Wow, that's really fast. Now we actually saw how fast sound travels. Let's go tell Dr. D.
Hey, Dr. D.
Oh, hi, kids.
Dr. D, I did this really cool experiment at school, and it showed that sound traveled so fast.
What do you think affects how fast sound travels?
Oh, you mean, what are the variables?
Ah, very good.
Could it have anything to do with the temperature?
That's a great question. The speed of sound increases with temperature. That's one variable. Another variable is the moisture.
I guess this means that on hot, humid days, when it's really sticky outside, the sound travels really fast.
No, not that much faster. The material that sound travels through, which we call the medium, makes a big difference. Generally, sounds travel faster through liquids than they do through air. They travel faster through solids than through liquids.
Why does that happen?
It's called elasticity. I'll show you how it works. While doing an experiment, Matthew, why don't you finish lining up the dominoes on the table, if you would, please.
Sure.
Bianca, grab a hold of this spring and hold on really tight. I'm going to send a wave pulse down the spring. Pay careful attention to how fast it's going. All right, now solids and liquids are more elastic than gases. See how much of a difference this makes? I'm going to increase the elasticity of this spring by increasing its tension. Elasticity tells me how fast things are brought back into place when they're disturbed. Are you ready? Watch carefully.
Wow, it's really moving.
Notice how the wave or energy travels through the spring, but the spring doesn't go anywhere. It just vibrates in place. It's like the dominoes that Matthew just set up. When he knocks over the first one, the energy will travel through, but the individual dominoes just move a little bit. Try it, Matthew.
Okay. Cool, now we know that sound gets softer as it travels away from a source.
When sound travels through a medium, the molecules vibrate in place, but don't really go anywhere.
What else do we know about sound?
While we know the medium affects how fast sound travels, we also know it influences how far sound goes.
But I thought we already talked about how sound died off in the distance when we were in that room with all the sponges.
Well, that's right. We discussed how sound gets softer with distance because the waves spread out.
Is that like when you throw a rock into a pond of water and the circles get bigger as they move away from the splash?
Exactly. But in addition to that, the medium affects how far sound travels by absorbing the sound energy. I have a friend over at NASA who specializes in acoustics. Her name is Dr. Christine Darden. You should go talk with her. She can help you to understand how the medium affects how far sound travels.
Maybe we can dial her up when we get back to the treehouse.
Thanks for all your help, Dr. D.
See ya.
Bye.
Bye, guys.